Good evening, everyone. This is the August novice meeting for the Houston Astronomical Society. My name is Chris Morisette, and for those of you that don't know me, I'm the novice chair for HAS. As I mentioned earlier, the presentation will be one of the longer ones. I've timed it at about an hour and a half, so grab some popcorn and hopefully stay tuned for everything. Um, Also, if you would, please go on mute. And if you have questions, go ahead and put them in the chat section of the Zoom call, and then we'll come back to that um, after the presentation is concluded. Okay, so here it is: cosmic clocks, techniques for determining the age of our cosmos. So I want to just say a couple of things first about the origin of cosmic clocks um, and that kind of thing. Um, I routinely do outreach events, and every once in a while we'll get questions about the age of a particular star cluster, galaxy, etc. And routinely, my answer is, well, how do we know? We go to Sky Safari. And that typically was the answer. And after one of these sessions, I thought to myself, well, that doesn't really, that's not really a very satisfying answer. You know, how can we tell the age? And as I dug into this, I found a really good story. It's not just one way to measure things, but it's really how the story is all about how we start out with radiometric dating and build from that. So I think it's a great story to share. And the other thing, as I was getting into this, we have a cosmic ladder for determining distances, which I thought is a really neat tool. And we've had presentations on the cosmic ladder. And I thought, well, gee, wouldn't it be cool to add a companion tool called the cosmic clock? So I'm going to unveil my version of the cosmic clock at the end of the presentation. The presentation today will be as follows. I'll provide an overview of the 9 different techniques that I'm going to cover tonight. We'll then dive into each one individually. At the end, on a slide called Building a Watch, I'm going to use that to kind of tie at least 6 of the 9 techniques together to see how they build on one another. I'll then unveil my cosmic clock, and then I want to say a word or two about references that I used for the presentation. So what are the techniques we're going to talk about here? And I've kind of got them listed in the order in which you would apply these depending on the distance that a particular object might be from us. So we're going to start out with radiometric dating and crater counting, and I've got those green because they really are applicable to our solar system. We'll then dive into 4 key techniques for determining the age of stars and star clusters, and that would be stellar spectroscopy, gyrochronology, magnetic activity, asteroseismology. Those are the 4 key ones for determining the age of stars, star clusters, things of that nature. I've got kind of a transition technique called dynamical age estimation, and I'm going to limit my discussion here to supernovae, uh, and specifically supernovae of a collapsing core of a star. And then we'll get into 2 of the techniques that we use to really go back in time and determine the age of some really old objects out there in our cosmos, which is redshift dating and cosmic microwave background radiation. The discussion tonight for each of these will be kind of a overview of the underlying principle of each technique, where you would apply this, what kind of objects you would apply it to. I'll give some examples of each where it has been applied, and then talk about advantages and disadvantages. So that's the structure for tonight's presentation. Occasionally, I'll cut away for a drink of water. And if I do, please don't let that be a distraction. I got a lot of talking to do tonight, so I will need water. Okay, so we're going to start out with radiometric dating. And I'm just going to move this up a little bit. So radiometric dating is all about finding a material that radioactively decays in a rock sample or a mineral sample that we would find here on Earth, or as you can see over here on the right, um, rock samples or samples we would get from meteorites, asteroids. We've been to Bennu and brought samples back, so they now qualify for this use of this technique. Lunar and planetary rocks, so think our moon and Mars, of course, our own Earth rocks. And I was surprised to find during the course of researching this topic that we've actually gone out and sampled solar winds. Apparently, there's fine grains of hard material in our solar winds. And this mission called Genesis actually went out, took samples, and then brought those back to Earth. And we were able to use radiometric dating to date the solar winds. So I thought that was pretty neat. A little bit more about radiometric dating, and I think first we've got to have a short discussion about an isotope. You know, what is an isotope? And this is kind of the key ingredient in any sample that we're going to need in order to radiometric date. So, an isotope is an element with equal number of protons but different number of neutrons. You'll see uranium-238 referenced in the talk here. They both have 92 uranium-238 and uranium-235 are different isotopes of uranium. They each have 92 protons, but differ in the number of neutrons. And if you add the protons and neutrons, you get the 238 and the 235. So certain isotopes of elements are unstable in decay into daughter isotopes at a constant and measurable rate. And that's the key thing that we're going to take advantage of when we use radiometric dating. This rate is quantified by an isotope's half-life, or in other words, the time it takes for half of the sample to decay. And that's how we're using the ratio of what they call the parent isotope to the daughter isotope, which is the isotope that is decayed down into another type of material. By measuring the ratio of the parent and the daughter in the sample, scientists can determine the age. And this technique will require a sample containing material that radioactively decays. Doesn't have to be the entire material, and it wouldn't be, but it would have that radioactive isotope in it. And then you'll also need a mass spectrometer in order to determine the ratio of parent to daughter and do the calculations to see where you land on the half-life curve. So this next slide is a kind of a generalized picture to kind of show you what this decay looks like. And you'll see here that I've got the percentage of the parent isotope left in the sample. And then as time goes by, the parent will decay down into the daughter. So in the case of uranium, here, and this table that you see down here on the bottom is an example of some, not all of the parent-daughter isotope pairs that you can utilize. But here we have, for example, uranium-238 and lead as the parent-daughter isotope. In this case, this isotope pair has a half-life of about 4.5 billion years, and the effective dating range is roughly the same. And so there are other pairs that we can take advantage of. It just depends on what the sample that we get from the meteor or from Mars or wherever. Just determines, just depends on what kind of parent-daughter pair we have in the sample that we bring back. And this diagram is really kind of cool. Just a little bit more about that. You'll see these red dots, which are the daughter isotope. You'll see those get more numerous in number as the sample gets older. And so this relationship right here is very predictable and very, very stable, and one that we can take advantage of to determine the age of a sample. Here is a picture of a isotope ratio mass spectrometer. I just kind of show this to give you an idea of what's involved here. On the left is an actual picture, and up here you can see this big chunk of black and green metal. That's our magnet. And the concept is relatively straightforward, although I'm sure the instrument's a little bit more complicated than what I'm making it out to be. But essentially, you're putting that sample, that isotope sample, in with a carrier gas that's coming into a chamber over here, and then it's pulled around this magnet. The lighter material will come out here, which would be the daughter isotope, and then up here would be the heavier material. And by measuring the ratio of those two, the daughter to the parent, we can tell how old the material is. Here's a couple of examples. The Allende meteorite was a meteorite that landed in 1969 in Mexico. Um, the scientists utilized uranium lead dating and determined that the age of this meteorite was about 4.56 billion years. So that was a really great finding. It was a nice finding because that roughly approximates the age of our solar system. And since that point in time, other samples from other places in our solar system have kind of backed up that finding to kind of give us a good ballpark idea of how old our solar system is, how old our sun is. Another example here is from Mars. We have collected Martian meteorites here on Earth. These meteorites are believed to have been ejected from Mars via some kind of large impact. That material flew our way, landed on Earth, and then we were able to retrieve those and use several different daughter-parent isotope um, pairs in order to determine the dating. And they found in these particular samples ages that range from about 150 million years, which is very young, to over 4 billion years. Lately, since we've been to Mars, we've been able to do some dating with actual material from the Martian surface. And in particular, here I'm pointing out the NASA's Curiosity rover that went to the Gale crater in 2013. They used potassium argon to do some dating here, and again, they found ages of materials to be about 4.21 billion years old. So we're beginning to build a picture of what the age is of our solar system. These are two examples of many. On the next in the next technique, we'll talk more about the moon because that plays a really key role. So what are the advantages and disadvantages of radiometric dating? So the advantages are, number one, it provides really accurate age estimates. The radioactive decay is very predictable and constant, so it serves as a really good clock. Can be used on various materials, including rocks and minerals, meteorites, and it offers a timeline for the formation and evolution of celestial bodies. Disadvantages, obviously, it requires the presence of suitable isotopes in the sample, and even more fundamentally, you got to be able to go get the sample. Samples can be contaminated and lead to inaccurate results. This happened on the Genesis mission. The landing didn't go according to plan and kind of crashed. A lot of the sample that was collected was destroyed or rendered useless. However, there was enough material left over that did survive and that they could use. And also, and this is a refrain you'll hear throughout the presentation, um, this technique requires careful sample preparation and analysis. So you've really got to know what you're doing. Okay, so that's radiometric dating. Now let's move on to crater counting. And crater counting in concept is a very straightforward technique. Applying it is a little bit of a more complicated story, but let's just start out with the high level view here. So here you see a nice picture of the Martian surface, and you've got this yellow boundary drawn around it, and inside you see a number of craters. And the concept here is that if you can count the number of craters in that particular area, you can equate that crater density, number of craters per square kilometer, to an age. Now, how we get there is a more complicated story, and again, I'll give you some more to chew on here. But the application of this technique can be used in several different spots on our moon, on Mars, Mercury, other moons, and even on asteroids. We can't bring samples back from every asteroid, but we can get some high resolution images that could allow us to use this technique. You'll notice I don't have Venus up here, and I will discuss that when we get to advantages and disadvantages. So crater counting assumes that the surface of a particular moon or planet accumulates impact craters over time, and that older surfaces have more craters and younger surfaces have fewer craters. And you can kind of see this over here in this little simplified graph that I show here for the moon. Early on in the creation of our solar system, we had a lot of construction debris crashing around out in the solar system. Therefore, early on in its creation, we had, on the creation of the moon, we had a lot of impacts. So the idea is that the more impacts we have in a particular surface area, the older that surface is. It will drop off as we clear out that construction debris and then level off, and we will have occasional impacts, but nothing of the magnitude that we had earlier in the creation of the solar system. So that's the concept. Older surfaces have more craters, younger surfaces have fewer craters. So scientists can estimate a surface's age by counting the number of craters and size of craters in a specific area, and then applying quote unquote known impact rates. Now, this is a key caveat because if we go and we look at different objects in our solar system, due to the position that they're in and the gravitational forces that are present in the area, different impact rates are going to be applicable. So think about Mars being out near the asteroid belt. You can tell on its surface that you're going to probably have more impacts out in that region of our solar system versus where we would be if we were on Earth or on our own moon. So you've got to you've got to apply these impact rates in order to get an accurate picture of things. How they do that, that's something that I really don't have a solid answer to, but that's part of the exercise. So again, this is useful for surfaces lacking accessible samples for radiometric dating. Okay, so let's talk about our moon because the moon plays a really important role here in terms of helping us calibrate crater counting. If you excuse me just a second, I'm going to take a sip. Thank you. And so here is a nice picture that shows the various Apollo missions to the moon. And you can see that rock samples were brought back from various locations on the lunar surface. As well, the Russians had an active program to go land on the moon and collect samples, so we have additional data from their space missions. And so what was done with that information is using those rock samples where we could radiometrically date the samples and then comparing those up with high resolution photos of the moon's surface where the rocks came from, we were able to build these calibration curves that gave us a relationship between the number of craters in a particular area and the age of those craters. And so these are 4 different calibration curves that were performed from various studies. You'll notice kind of a gap here in data right here. Um, that is a gap and probably is going to be subject to introducing some error. However, it is relatively flat, so maybe it's not as bad as it appears on the graph. We do have samples, older samples here, and then more samples down in this neck of the woods here. So those are the calibrations that we've done using the rocks, radiometrically dating those, and then pairing those up with high resolution photos from of the areas that the rocks were extracted from to get these calibration curves. So where have we used it? Obviously, we just talked about the moon. We've extensively applied it there to determine the age of various areas of the lunar surface. We can calibrate crater density with radiometric aging using samples from various space missions. And then this lunar calibration is the foundation for dating surfaces using crater counting. So if we're going to apply it to, say, Mars, or even in the next example, Europa, we've got this foundation from which we can start and build on. So another example of where we did use crater counting was on Europa, and we used the Galileo spacecraft to do that crater counting. And here, crater counting was employed and revealed that the surface of Europa was geographically young. There were a very low number of impact craters, indicating an average surface area of only 40 to 90 million years, which is really young. And so what this suggests to us is that Europa has active resurfacing processes, possibly related to its subsurface ocean or cryovolcanic activity. So in this particular case, we weren't able to use crater counting to determine the absolute age of Europa, but we were able to get a handle on the surface and get an understanding of, what some of the processes, active processes that are happening on Europa. So that's another example. We've used this on Mars as well, and I don't know if they used it on Mercury, but that would certainly be a good candidate. So what are the advantages here? Well, the key advantage here is it does not require physical samples. So, you really simplify matters in that respect. It can be used on various solar system objects, so asteroids, planets, moons, and we can use our lunar surface as a calibration standard. It's not perfect, and it really serves more as a method to help, as a secondary method to help us validate other measures that we've taken. One being with radiometric dating. The disadvantages. So if you have a celestial body with a dense atmosphere, that can hinder impact detection. So Venus is an obvious thing that comes to mind here. You got a very thick atmosphere. Getting high resolution photos is probably out of the question. Resurfacing or erosion can modify or erase craters, so that's an issue. And then distinguishing between primary and secondary craters can be challenging. So, crater counting is not perfect. It may not be the most accurate method, but it does give us another tool to go out and look at other objects in our solar system and at least validate the findings that we've found, and build on the findings that we've gotten from radiometric dating. Okay. Okay, now we're going to move into the four star-related um, techniques. And the first one we're going to discuss here is stellar spectroscopy. And that's a very well-known um, technique applied liberally throughout the scientific community, the astronomy community. And just talk a little, excuse me, I'll just talk a little bit about the concept here, for those of you that may not be familiar with spectroscopy. So what we do is we look at incoming light from a particular star of interest. And in this case, we would let that light come through a hole or some kind of a plate so that we could isolate the star light that we're looking at. And then this starlight would be bounced off a special grating or a prism or something of that nature that would split the light into the different wavelengths. And that split light is then focused onto a detector of some sort, forming a spectrum. And a spectrum would show both emission and absorption lines. Now, this technique can be applied, it works best, let me state it that way, for solar type main sequence stars, subgiants and giants, star clusters, nebulae, and then I've got in quotes here young stars, the quote or the italics with the underline, meaning that while it can be applied to that, it's probably not as accurate as it would be for these other things that I've listed here. You really can apply this to any kind of star, but the accuracy of the measurements are going to vary. And what you see listed here are really where we can get accurate measurements. So From this page, we go down here, and this kind of shows you what those spectrums would look like depending on the class or type of star that we're looking at. And you can see from the absorption lines that we can tell which type of elements are there. We can measure the temperature, and from that information, we can deduce the luminosity. We've got the distance measurement to the star, and we can also infer the mass. So that is kind of the bottom line result that we can expect to get from spectroscopy. And then once we've got that data, we can plot those points here on the HR diagram. And so you see over here on the x-axis, here's where the type of star is that we found from our spectrum. Here's where we would plot it on the x-axis, and then on the y is where we would plot luminosity. And so you can see here that I've got the surface temperature, the luminosity. In the previous slide, I've got a good idea what the composition of that star is, and then also I can understand what the mass of that star is. However, you'll notice here in green these age indicators, which is in this case is the main sequence lifetime. And that's the piece that kind of puzzled me is like, well, gee, I can understand how everything else got here. Where did these ages come from? And so that's the key discussion here. So let's walk through this a little bit more in detail. So again, the pattern and strength of the spectral lines provide insights into the star's temperature, composition, and luminosity. And to get luminosity, you're going to need distance. Combined with mass, which can be inferred from spectroscopy or measured directly if a star is a binary, theoretical stellar models can be employed to calculate the age. Okay, so when we get to that point, kind of a trigger goes off in my mind, or a red flag goes up. Well, gee, now we're relying on models. And the question I had was, well, should we be confident in these models? And the answer to that is yes. And here's why. The core principles of gravity, nuclear fusion, and radiation transport are well understood in physics. And I'll just kind of take a short detour here. A few years ago, I visited Los Alamos in New Mexico, and I went up to the Bradbury Museum, which is a museum dedicated to nuclear weapons program. It starts with history on the Manhattan Project and brings you up to the current day. It's a fascinating museum. If you're ever out there, I highly encourage a visit. Anyway, part of the discussion there, presentations that I saw, uh, said that they were able to substitute actually detonating a explosion with a nuclear yield, i.e., nuclear radiation. They were able to substitute doing that by using modeling. And if you think about a hydrogen bomb is all about nuclear fusion, and so is the process of a star burning up its fuel inside inside of the star. So the point I'm trying to make here is that we have used modeling, and it's not 100% modeling. There are still other things that happen, but that modeling has gotten so good that it was able to provide a guarantee or a vote of confidence in the robustness of our nuclear weapons stock. So I thought that was an interesting point. Secondarily, models reproduce the sun's spectrographic properties, and the sun is our best age-calibrated star. We had all that data from meteorites and the solar winds, crater counting, all that good stuff has really given us a good idea of how old our sun is, which is about 4.6 billion years old. And knowing that from other methods has given us a check, if you will, on these models. And then the final one here, before I read this thing, let me talk a little bit about star clusters and this concept of main sequence turnoff. So star clusters are really important tools for us to understand the age of a star. Star clusters have the following characteristics. Number one, the stars that are created in a star cluster come from a common cloud of nebulosity. So they're going to have the same composition. They're going to be of the same age. Granted, they're not going to be exactly all the same age, but over the course of the entire lifetime of a star, the differences are pretty minuscule. So they're of the same age. They will be of different size and mass, so we have an opportunity to see when stars begin to turn off of the main sequence. So this whole concept of main sequence turnoff, what this means is if we have a star cluster and we see that the last remaining stars that are still on the main sequence are still there. We have a really good marker for the age of those stars, of all of those stars. And so going back here, if you think about it, if you're at a star cluster that has these type B stars here, and you see that most of these have turned off, and that their last few are remaining here, this 10 to the 8th years is a good marker. Okay, so again, we're relying on a model, so the argument's a little bit circular, but by observing the main sequence turnoff point of stars from multiple star clusters of different compositions and ages, we can further validate model results. So if we have a model that we can run against all kinds of different star clusters and still get the same result for that that point at which the main sequence turnoff occurs, then we got another means to validate our models. Okay. Typical accuracy, if you have stars or star clusters with good data, you can get accurate age ranges of 10 to 15%. However, it's less accurate for field stars. Often accuracies of 20 to 30% here, so not as accurate there. And we'll talk more about some other methods that can help us understand those field stars. Here is a slide that I found that has a bunch of space observatories, along with kind of a general placeholder for ground-based observatories. So I wanted to show you this to kind of give you an idea of the type of equipment you're going to need in order to get those spectroscopy readings. So we can get them from ground-based observatories as well as Hubble, Gaia, and Webb. So just to kind of give you an idea of where we can get that data. And then also this collection of space observatories, most of these deal with, if not all of them, deal with exoplanet research. And in a little bit, I'll tell you why those are well suited for the type of techniques that we're looking at. So here's a couple of examples where we've used spectroscopy to measure the age of star clusters in the case of Pleiades. Here again, we use spectral types, temperatures, and luminosities to kind of plot where Pleiades is on the HR diagram. We've determined the point on the HR diagram where the last remaining stars are still on the main sequence. And then from that, we've concluded that Pleiades is about 100 million years old. And Pleiades is made up primarily of type B stars, which are large stars, and not very well suited for measurement by just a single type B star being determining the age with spectroscopy. However, in a cluster like we have with Pleiades, we can use spectroscopy to get an accurate age reading. For younger stars, we use spectroscopy, only not in its classical traditional way. So let's talk a little bit about the Orion Nebula. Here we have our closest massive star-forming region to Earth. And what we've seen here is that the young stars in the Orion Nebula have strong lithium absorption lines. And the presence of lithium is something that is strong in younger stars, but as these stars mature and become mature and get onto the main sequence, that lithium is destroyed. So if we run into stars with strong lithium absorption lines, we can make some assumptions about how old those stars are. And in the case of the Orion Nebula, these are in the neighborhood of somewhere between 1 and 3 million years old. This method provides a range and not a precise age, but it is a tool that we can use for young stars. So what are the advantages of stellar spectroscopy? It offers insight into a star's composition, temperature, and evolutionary stage, and can be applied to a variety of stars and star clusters. The disadvantages is it requires high resolution data, so it's resource intensive. Age estimates do depend on theoretical models of stellar evolution. However, hopefully I've convinced you that those models are fairly robust and we can hang our hat on them. And then interpreting spectra can be complex, requiring advanced knowledge and computational tools. So those are some of the advantages and disadvantages of stellar spectroscopy. Yep. Now let's move on to gyrochronology. And gyro, or turn, or like a gyro top, means, in this context exactly what it says here. What we're doing is we're equating the rotation of that star with its age. So if a star has a quote unquote high rotation rate, in other words, uh, times per day of the period of that rotation is fast, then we can assume that's a young star. As it ages, though, it will slow down, and then that's the marker that we're using in order to determine the age. So if you excuse me just a second, I'm going to make another sip. Thank you. Now here we can apply with with confidence gyrochronology to solar type main sequence stars. Here we can use it on field stars, so they don't necessarily have to be in clusters, and we can also apply it to open clusters. So that's kind of the nice feature of gyrochronology is we can look at an individual star that may not be in a cluster. So here's what happens here, just to kind of dive down a little bit more on gyrochronology. So stars will spin down over time. And there's this concept called magnetic braking that I will describe here in the next slide that accounts for that spin down. And so by measuring a star's rotation, we can estimate its age. We do require photometric data from space observatories. So this brings me back to that picture of all the exoplanet-related observatories in space. They're well suited to do this kind of work because you need photometric data to determine the rotation rate of a star. We can't look at it like we would our sun and just watch sunspots go around. We have to look for dimming, and the cameras and equipment they use to detect exoplanets fit the bill quite well for determining the spin rate of stars. It's an effective method for low mass stars, so spectral types F or lower, and it's less effective for stars that have not yet reached the main sequence, have evolved off the main sequence, or have some kind of unusual magnetic activity or some other factors affecting its rotation. So perhaps a binary star system would not be a good candidate for using gyro rotation or gyrochronology, excuse me. Okay, magnetic braking. So this is a phenomena that I have spent a lot of time trying to figure out. I had some discussions a couple of weekends ago with a colleague of mine from HAS. We talked about this, and I think I've got the story straight or the picture right here. And let me see if I can explain it to everybody here. So, what is magnetic braking? So as a star rotates, just like a generator or a dynamo, it does generate a magnetic field. Stellar winds come off of a star as well from just the boiling and the turbulence on the surface of the star. And the point at which this material from the stellar wind, the kinetic energy from that equals the magnetic field strength is this point called the Alfvén radius. And what happens is at this area right here, Some, but not all, stellar wind material will collect and will form a mass out here that is rotating along with the sun. So these magnetic fields rotate with the sun, and by virtue of that, it's carrying this captured stellar wind material. Okay, so what you've done in effect is you've changed the moment of inertia of the sun. And the best analogy that I can give you to kind of describe the phenomena here is the classic ice skater. So if you're watching the Olympics and you see the ice skater pull her arms in tightly, she will spin fast. If she moves her arms out, her rotation will slow. And this collection of stellar winds out at this Alphen radius is that effect of the skater moving her arms out. And that's what's slowing down the motion of the star over long periods of time. This doesn't happen quickly. It happens over hundreds of millions, billions of years. So that's the phenomena. And that's important not only for gyrochronology, but for the next two techniques that we'll talk about. Here again, just to give you an idea of what observatories are involved in doing gyrochronology studies, Kepler, TESS, and Gaia. And again, these are exoplanet uh, observatories as well. And then here's an example that I wanted to show you. This is a star cluster NGC 16 or 6819 that is about 2.5 billion years old. So using data from the Kepler mission, astronomers measured the rotation periods of 30 solar type stars in the cluster. And by applying gyrochronology models, they were able to determine the age of the cluster to within an uncertainty of about 10%. So here is an extract of that study I got from a blog called Astrobytes, and this was written by a graduate student um, from Harvard. Uh, I think he went to UCLA and then Harvard, Anson Lamb, and he actually did this study with that sample that was from Kepler. So what you see here in this graph is a model that shows us how we can determine the age of stars of differing mass from a star cluster. So here's our star cluster NGC 6819. Let me talk a little bit more about the axes here. So here we have the photometric color index for each of those stars, which is not as detailed or refined a measurement as spectroscopy, but it can give us um, a fix on the mass of a star. And then here, along this axis right here, you'll see the age, and I'll get back to that in a second. And then here's the rotation period here. So this model kind of looks like a sheet. And the reason it does is because the rotation period for stars that are in that cluster, which all have the same age, like we talked about earlier, but have different masses. So you see 1.2 solar masses, one solar mass, and then 0.85 solar masses. We also have some calibration points from NGC 6811 and from the Hyades cluster. So this model, this sheet is our model that we're using, and this blue line is the data set. So if we follow this over to here and we drop down to the age axis, that is where we're getting the 2.5 billion year age for that star cluster. And again, it's kind of got that funky shape because we're talking about stars of differing masses. Here is another graph from the same paper. And here you can see this data set here is from the blue line that was on this page here. And the message behind this data set here is to show that there is a good correlation between these low mass stars in NGC 68, or excuse me, yeah, 6819 and the model. Yep. So that is the data from the study. So the advantages of gyrochronology. It does provide age estimates with uncertainties that are typically around 10 to 20%, so that's pretty good. It can be applied to a variety of stars, including those not in clusters. And it can be calibrated by using the known age of the sun and other star clusters, stars and star clusters. So we've got data here that can provide that calibration, much like we use radiometric dating of samples from the moon. Disadvantages: it is limited to main sequence stars, depends on precise measurements of rotation periods and color indices, hence the use of the Kepler and TESS space observatories. And then it does rely on empirical models that may have some uncertainties. So there's always an element of that as well. However, it is a very useful technique and can help us double check age estimates that we get from spectroscopy. The next technique we're going to talk about in the solar or star range or realm is magnetic activity. And the idea here is fairly straightforward, and that is as a star ages, its magnetic activity decreases. It works best for solar type stars on the main sequence, and it can be applied to red giants, but it's not as accurate. And then here's the idea behind magnetic activity. So what we're doing is, stars with a convective outer layer, like our sun, generate magnetic fields. As stars age, magnetic activity decreases due to slowing rotation. So go think about magnetic braking. We've got that phenomena happening. That's slowing the rotation. That's decreasing the magnetic activity, just like a dynamo or a generator at a power plant. By observing the level of magnetic activity, a star's age can be estimated. So the older the age, the lower the magnetic activity. The lower the magnetic activity, the weaker calcium ion emission strength is. And that's one of a couple of different measures we can use to determine the strength of a magnetic field in a star. So this does require high resolution spectrometers and photometers to measure this calcium ion, and specific the H and K lines. You can also measure H alpha and H beta Balmer lines, and you can use X-ray and ultraviolet emissions to get a handle on the magnetic strength of a star. Again, just same story that I mentioned earlier. We're using Kepler and TESS. And by the way, I just want to make sure these are not all of the devices that have been used, but examples in order to kind of give you an idea of what it is you need in order to take these measurements. So a couple of examples here. Excuse me just a second. I'm going to take a sip. Here is a study by a person by the name of Szymanich back in 1972, and this became a benchmark for magnetic age calibration. And what he did in this study is he established time scales between ionized calcium emission decay, rotational braking, and lithium depletion. He made the study observing stars in Pleiades, Hyades, Ursa Major, and our own sun, and he found that the magnetic activity, as measured by calcium ion emissions, decreases with the square root of the stellar age. So this relation is now called the Szymanich law, and it underpins most magnetic activity-based age models. So the calcium ion method is the one that he focused on closely for this study. Another example has been the Hyades Open Cluster. It has been extensively studied, not only for magnetic activity to determine its age, but also gyrochronology and spectroscopy. But in this particular, regarding this particular technique, the study has concluded that Hyades is about 625 million years old, and that individual stars from Hyades have been used as calibration points in other magnetic activity studies. So it's been used in other studies. And then here's an example, an excerpt from the schematic study, and I have here in the red dashed oval the concentration of calcium ion decreasing as the years go by. And that was the main conclusion from the schematic study. So what are the advantages here? You can apply it to, a wide range of stars. Again, your, solar type main sequence stars are going to be the primary beneficiary of this technique. And it can be used with other methods for more accurate age estimates. So this can be used again with gyrochronology and with spectroscopy to, get a check on what those different techniques are telling us about a star's age. Disadvantages, it's less effective for young stars as magnetic activity is still increasing, requires high quality long-term observational data, again, resource intensive, and empirical relationships may have uncertainties, especially for stars with unusual magnetic properties. So again, you've got modeling, you've got relationships that can introduce a source of error. The last technique we'll talk about with respect to stars is asteroseismology. And just a kind of an editorial comment here. This one took me the longest time to really wrap my head around because how you figure out seismic activity on a star was a real mystery. But I'll attempt to give you my understanding here tonight, and hopefully that'll make some sense. So at a high level, the concept here is that, well, the underlying concept is that stars do oscillate. The surface of a star will oscillate. And as a star is aging, the amplitude and frequency of those oscillations decreases. So that's the overriding concept. This application can be used uh, effectively with solar type main sequence stars, subgiants and red giants, and with binary stars. Because here you're not relying, you're looking at the surface of the star as opposed to the rotation of the star. It can also be applied with some success to large B and A type main sequence stars and to white dwarfs. And white dwarfs are a particular area of fascination here, and I've got an example that I think you'll find pretty interesting. Okay, so what's going on? First of all, it's astroseismology is akin to seismology on Earth, and that is we've got oscillations that are happening in a star. And these oscillations are caused by turbulence near the surface from boiling and from the rotation of the star. And you're also getting oscillations from pressure and gravity waves pulsating inside the star. Now, in solar type stars, the pressure waves are the ones that manifest themselves on the surface of the star. The gravity waves are down deep in the star in the radiative zone, so we really don't have an ability to see those in a solar type star. However, when we get to white dwarfs, we will be able to see that, and I'll talk a little bit more about that here in a slide or two. So stars exhibit various resonant modes and frequencies of oscillation, and that's what we're trying to measure and pull out of our observations. And so by analyzing these oscillations, astronomers can infer the age of the star. So this requires ultra-high precision photometry to measure measurements over extended periods of time. And then you also need different spectrographs than what we typically would employ. There's a spectrograph called a shell spectrograph that has very high diffraction and fine dispersion capabilities, and we use that to measure radial velocity variations. So it does take some more sophisticated equipment than what we would use with spectroscopy. This method is less effective for stars that have not yet reached the main sequence or are exhibiting complex or atypical oscillations that are difficult to model. Okay, so and then again, of course, I've got my space observatory slide. And again, here are some of the observatories that have been used to do astroseismology studies, Kepler, TESS, and Plato. It has been performed from ground observatories, but these are the main devices used. Okay, now what's going on inside this star? I've got this cutaway of a solar type star, and here you see these pressure waves here that are standing waves and that are manifesting themselves on the surface of the star. And then down here, you've got the gravity waves that are confined to the radiative zone. So what is it that these pressure waves are? Is there an analogy that we can use? Um, my wife's a piano player. I'm not the musician in the house, but she is. And when she plays a C major, she's actually playing three different keys on the piano. She's playing a C, an E, and a G. Memory serves me right. Now, there are multiple different types of C major chords that you can play on a piano, but we'll just pick one. And when she plays that chord, you can hear the sounds, which are pressure waves, floating around in the atmosphere and collecting on our ear to make a beautiful sound. We'll also, in addition to getting that one chord that she plays, we'll be getting other harmonics. So there'll be other tones of chords that will come out. And that's kind of the idea of what we've got here in our sun. We are getting um, we're getting multiple pressure waves that are showing up in a as oscillations on the surface of the star. Okay. So that's happening. And then as the star is aging, it's burning up fuel. And as it's burning up fuel, it's really changing the structure and the density of that convection zone. And so just to kind of dive into this a little bit more in detail, inside the core of a star, hydrogen is gradually being used up. That core will shrink and it'll heat up, which will cause the outer layers to expand slightly and cool. This will shift the star's internal structure, which affects how pressure and gravity waves travel. Frequencies shift as the star's density changes. Natural oscillation frequencies get lower, and amplitudes will drop as the magnetic activity and rotation of the star decreases. Remember, these stars will break over a period of time, so uh, you won't have as much turbulence there, and that will result in less energy available to excite these oscillations. So that's what's happening as the star is burning through its fuel, its structure and its density is changing, and that's what's affecting these oscillations. And at bottom line, the oscillations are becoming quieter. Okay. So this next slide shows you a measurement of the indicators that we're looking at, velocity and brightness changes. And you can see here, I'll talk a little bit about this. This gray set of information here is all the data that we're pulling off from our space observatory. And then we're applying a Fourier transform to actually pull out these uh, standing waves that you see here at these different frequencies. And then here on this axis here, they've got this parameter called spectral density, power spectral density. To me, that's really just kind of the intensity or the amplitude of these waves. And then in this particular case for this star 16 Cygnus A, we're looking at four different pressure waves here, and you can see these squares and triangles and circles and diamonds showing you where the harmonic oscillation of these pressure waves is occurring. A lot of stuff to kind of wrap your head around. I think the message here is when we're going out and we're measuring these oscillations, this is the data that we're getting. We're finding the frequency at which these waves are occurring at and the intensity of those waves. So just to kind of recap here, this density plot really is showing you the power or intensity of time variable signals like brightness or radial velocity and where it occurs across multiple frequencies. These peaks reveal oscillation modes of standing pressure or gravity waves. In our case, it was pressure waves. And then by analyzing the wave spacing and distribution, that provides insight into the star's internal structure and allows determination of properties like mass, radius, and age. Again, tough to get your arms around in a novice presentation meeting, but I guess the bottom line message here is you take a snapshot of these oscillations, and by virtue of doing other studies, you can compare the frequency and amplitude of these oscillations to other stars that are older, and then use that as a way to gauge the age of the star. One last thing here, there is a lot of background signal from convection, rotation, and photon noise that has to be filtered out. And this diagram here just kind of shows you some of some of the noise that has to be filtered out. So here are the oscillations that we're interested in. And then here are other uh, oscillations that we're getting from granulation, from sunspots or star spots, and then from photon noise. So the only thing I'm trying to say here is there's noise that we have to extract, and you get it from these different sources here. Okay, so a couple of examples. M4 is a globular cluster in Scorpius. It's one of the targets that we had for our summer objects, gems of the summer sky. And then using data from Kepler, astronomers detected acoustic oscillations or singing in ancient stars within the cluster. And then by analyzing these oscillations, they determined the mass and age of the stars. And in this case, those stars turned out to be very old, about 11.5 billion years old. Um, there was a study and a presentation that I saw back in February by a PhD student at University of Texas at Austin, Malia Kao. And what she was doing in her study, she was trying to use white dwarfs to get an estimate of the age of our Milky Way. And white dwarfs cool slowly over time, so temperature and age can be correlated. And we didn't talk specifically about using temperature, but that's what she was using as the measurement to tell how old these stars were. Recent observations show that these white dwarfs undergo crystallization. And this process releases heat, thereby making the dwarf appear younger than it actually is. So think about water freezing into ice. It's going to level out, and you're going to get that heat released by the phase change that the water is going through. So Malia had to do some work in order to fill in the gaps during that crystallization period. And what she was able to do is find crystallizing pulsar or pulsators that offered an opportunity to apply astroseismology in order to refine these models for aging of white dwarfs. And in this case, she was actually measuring the G mode oscillations. And I think she was able to do that because the star is shrunk down a lot, and the outer convective layer was thinner and denser than what we have in a main sequence solar type star. So the gravity waves were actually, you're able to actually see those gravity waves on the surface oscillating. So as part of her research, Malia used the Gaia Space Observatory and the Otto Struve telescope at McDonald to expand the sample size of these pulsating white dwarfs from 7 to 24. And that will be key to her research because increasing that sample size will allow her to refine the aging models for white dwarfs and, eventually get a more precise handle on the age of our own Milky Way. So I thought that was really interesting work that she's done. And here is a HR diagram. Excuse me, I'm just going to take a quick sip. Here's an HR diagram that kind of shows you the areas that she was looking in order to find these pulsators. So up here you see a band of pulsating white dwarfs that are helium, carbon, oxygen dominated. have in their atmosphere. Here's uh, a band of white dwarfs that are hydrogen dominated, and then down here a band of white dwarfs that are helium dominated. So I just showed you this to kind of give you an idea, where she was looking in order to find these pulsating white dwarfs. So what are the advantages of astroseismology? It provides accurate age estimates with uncertainties typically around 5 to 10%. So that's very accurate. Offers detailed information about a star's internal structure, composition, and evolutionary state, and it can be applied to a wide range of stars, including those in various evolutionary stages. Disadvantages, it does require high precision instruments and extended observation periods, again, making it resource intensive. You still have theoretical models of stellar evolution that you have to rely on, and it's not very effective for young stars or stars with irregular oscillation patterns. So kind of the same story for the as we discussed with the other techniques, but those are the advantages and disadvantages of astroseismology. Now, before we pivot out of stars, I just wanted to talk a little, just kind of provide a summary, if you will, of the four different techniques. And this is just kind of a one-pager to kind of give you an idea of the techniques, where they apply, and what kind of age range we can derive from those. So spectroscopy and astroseismology are really the most versatile and cover the widest range. And then gyrochronology and magnetic activity help us with younger stars. So that's just kind of a summary here before we pivot and move on away from measuring the ages of stars. So next we'll talk about dynamical age estimation. And this is one of my favorites here because it's real simple and I can understand it. So that's got a lot going for it there. So I'm going to talk about this in relation to supernova remnants that have resulted from a core collapse. So, think a black hole or neutron star after a large star collapses and implodes on itself. So the idea here is very straightforward. You have this expanding shell of a supernova remnant. You have this expansion velocity, and just by dividing the radius by the expansion velocity, I'm sure with some other parameters thrown in there as well, you can determine the age. So it's really straightforward. Again, that's the basic concept. Is the age is proportional to the radius of the remnant divided by expansion velocity. The method does assume the remnant has been expanding at a measurable and predictable rate since its explosion. And you have to make corrections on your calculations depending on whether the expansion is decelerated due to interactions with other interstellar material. So that's the idea. Again, here are some of the uh, observatories that we can use to take these measurements. And so ground-based Hubble and Webb are just examples of those space observatories. Here's an example, Cassiopeia A, which was a type 2b supernova, well-studied supernova remnant, about 11,000 light years away. They measured the expansion velocity by looking at the Doppler shifts in spectral lines from optical, radio, and X-ray observations. So that's how they were able to measure the velocity. And then the current radius was determined by looking at the angular size of the remnant and estimating its distance. And so, I'm doing it is much more difficult than explaining it here in this high-level talk, but, pretty straightforward to understand. And from those calculations, they were able to estimate that this remnant was about 350 years old, which was consistent with historical records of a supernova in the 1670 to 1680 timeframe. So that's the cool thing about this type of, uh, of search and age estimation is you can go back to written records to tell if in fact your estimates are accurate. Crab Nebula is another example of something where we have written records from the 1200s that, again, can be used as a validation of our calculations. We've used Hubble and Chandra to confirm the expansion and help refine the age using both constant speed expansion and decelerated models. So our new technology in space has helped us to better refine those estimates. So that's dynamical age estimates. What are the advantages? So it provides a direct physical estimate of the time since the explosion. No modeling here. Works well for young supernova remnants with measurable expansion. And again, it's independent of stellar models or nuclear physics assumption. And that's kind of the beautiful thing about it. That's the thing that appealed to me. Disadvantages, it does assume symmetry and uniform expansion, and that's often not the case. So you have to get in there and make corrections. Interaction with dense atmospheres can slow or distort expansion. So that can, again, need to be compensated for. And then it requires accurate distance measurements in order to determine the size of the remnant. So that's dynamical age estimate. It's kind of star related, but it's really kind of the age of the death of a star, so to speak, at least in the example that I discussed here. We'll move on to redshift dating. And again, this is pretty straightforward as well. We're using redshift dating to determine the age of very distant objects. So think galaxies, quasars, can be used for supernova type 1A or type 1A supernova, galaxy clusters, and gamma ray bursts. So this is a technique that allows us to reach far beyond our own Milky Way. And the concept here is relatively straightforward. We're taking a spectral reading of the object in question called the observed spectral reading. And then we're comparing it, or comparing these absorption lines here to what we would see at rest or what we would see in a laboratory. And then by subtracting these two wavelengths, dividing it by the at-rest wavelength, we can come up with this factor called Z, which gives us an idea of how old a particular spectrum of light is. So again, the concept here is we're measuring how much light has been stretched or redshifted due to the expansion of the universe. The higher the redshift, the farther the object, the longer ago the light was emitted. And so this will require spectrographs to measure the light from for the spectrum of the light from the distant source, simulation models to translate redshift into age. And then I've got just kind of a simple, straightforward process. You measure the spectrum of light, you identify the spectral lines like hydrogen and oxygen and compare that to an at-rest or rest frame wavelengths of the same elements, calculate the redshift, and then use a cosmological model to convert that to a redshift age. So it's more difficult than I've made it out to be, but conceptually it's a pretty easy thing to kind of get your head around. Again, here are the tools that we've used in order to get the data that we need for redshift analysis. And then here is an example of a galaxy that was age dated using redshifting. GNZ11 was detected by the Hubble Space Telescope. It had a redshift factor Z of 11.1, meaning the light was emitted just 400 million years after the Big Bang. It's one of the oldest and most distant galaxies ever observed, and redshift dating was key in determining when its light was emitted. And so here's a nice little pictorial. You kind of see the previous record holder here, and then here is GNZ11. And here's our Hubble Space Telescope out here with modern galaxies. And then you can see that this artifact was way back into the early part of the creation of our universe. So what are the advantages of redshift dating? It can date very distant objects. There's no need to resolve stellar populations. So, the farther out we get, the more difficult that gets. Certainly with the large and small Magellanic Clouds, which are companion galaxies, we can resolve stellar populations. I think this is even possible with Andromeda and Triangulum, but as you get further out, you're really just looking at a blob of light. So that's the nice thing about redshift dating. It does require high quality spectra, and redshift can be affected by motion other than cosmic expansion, um, such as Doppler redshift, which is really motion of objects that move in relation to the observer but aren't necessarily attributed um, to the expansion of the universe. So Andromeda. Andromeda is moving, it's moving towards us, and that movement is not related at all to the expansion of the universe. Binary stars are another example of this as well. Runaway stars out in our own galaxy, X Persei near the California Nebula. Those are examples of Doppler redshift that we can run into. Gravity redshift is another example. So light escaping from massive galaxies or galaxy clusters, it's overcoming all that gravity, and just by virtue of that, the energy that that light is takes to escape that is being affected and is redshifted. Black holes, stars around black holes, etc. So just a couple of disadvantages here on redshift dating. Okay, we're almost done. So bear with me. One more technique and we'll cross the finish line. Here is cosmic microwave background radiation measurement. And we use this to get a handle on the age of our universe. Um, I thought this was really, one of the benefits I got out of putting this presentation together. I had always heard about CMB, kind of knew about it, and thought I knew about it. But as I was digging more into this, I got a better appreciation for, what it's all about. So I'm going to read this slide, and I hate doing that, but this was new material to me, and I just want to make sure I get it right. So the afterglow of the Big Bang represents the earliest detectable radiation in the universe. Approximately 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms, allowing photons to travel freely. These photons, now stretched to microwave wavelengths due to the universe's expansion, form the CMB. By analyzing the temperature fluctuations in the CMB, cosmologists can detect can detect density differences. So cooler areas are areas of higher density, warmer areas are areas of lower density. And and this is the key thing, these density differences are thought to be the source from which galaxies and other large scale structures developed. So the CMB fluctuation pattern is basically used in different cosmological models, one prominent one being the lambda CDM model, to see if the results match the structure of the cosmos we have today. So in other words, they're taking this pattern, they're feeding it into this model. They're letting the model run from, 380,000 years after the Big Bang up to today. And then they're taking a look to see if the results give us any kind of match to the structure that we have in our cosmos today. And then if it does, we can infer or derive the age of the universe from that from that model, from the pattern being fed into that model. Now, we don't use the space observatories that we talked about earlier here. We have special space observatories that go after and measure the CMB, and here's three of them. So the Cosmic Background Explorer, which I think was sent up in the early 2000s, came back with some initial readings on these temperature fluctuations, and this was the pattern that it came back with. So it did pick up a discernible pattern, but it's really kind of fuzzy. The Wilkinson microwave probe went up some years later and got a much more detailed view of the pattern. And then the Planck satellite here, even more recently, gave us back with an even more detailed pattern. So if you can get a more detailed view of that pattern, then you can use that as input to your model. And and by running the model, seeing if what you get out of the model matches up with what we observe today. So about a year ago, I was in Stockholm, Sweden, and I went to the Nobel Prize Museum in Stockholm. Lovely city. If you ever get a chance, go. I love it. I wish I was there now because it's probably nice and cool. Anyway, I digress. What you see here is an artifact that was donated by George Smoot, and he was on the team that was involved with the Kobe satellite, that first one that went up. And this device that you see pictured here is what actually was used to measure the microwave or measure the cosmic background radiation that developed that pattern. So this was a prototype, and apparently award winners to the Nobel, people that receive a Nobel Prize will make these artifact donations, and this is the one that George Smoot um, donated to the museum. It's not a very complicated looking piece of device, but that's the measurement tool that they used. So the advantages of this method, it offers insight into the universe's composition and expansion history. It enhances the understanding of fundamental cosmological parameters. Disadvantages, it does rely on the accuracy of cosmological models and assumptions when translating observations into age. I might also add there's research that has just concluded out at the Hobby Eberly telescope, the HET dark energy experiment that the results of that are at a minimum going to aid in refining these models and conceivably upending these models. So we'll see what happens, but that's research work that's going on here in Texas that is going to have an impact here. And as with all the other techniques, it does require a complex data analysis and interpretation. So kind of a recurring theme throughout the presentation. All right, we're almost done, guys. So this is building a watch. So radiometric dating has allowed us to accurately estimate the age of meteorites, solar winds, the Earth, Moon, and Mars, which has given us a good idea of the age of our sun and solar system. Material from the moon has allowed us to develop and calibrate crater counting as a method to estimate the age of objects beyond practical reach for sample collection. Using crater counting, we've expanded our ability to estimate the age of other objects in our solar system, such as asteroids and moons orbiting other planets, which has further refined our estimates of the solar system's age. By studying our sun and the stars, we have been able to calibrate or develop, calibrate, and refine methods like spectroscopy, gyrochronology, magnetic activity, and asteroseismology, which has aided in estimating the age of distant stars, star clusters, nebulae, and the Milky Way itself. Additionally, dynamical age estimation has allowed us to estimate the age of supernova. Redshift dating has provided a means to expand our age estimates to objects beyond our Milky Way, such as distant galaxies and quasars. And finally, CMB radiation measurements has allowed us to estimate the age of the universe. So I thought this was kind of neat to kind of show you the ties and the story that had kind of been built up over the last century or so. And I like it when stories like this are connected. So I wanted to share that with you. Okay, so here it comes now, the cosmic clock. And I know what you're thinking. An engineer must have designed this thing because it is boring as heck, but guilty as charged. Anyway, I had to come up with something. So you can see here that I've got different bands that are related to the different techniques, and I have listed here the various examples that I went through. So pretty self-explanatory. You've got dynamical age estimation with this small sliver right here, magnetic activity here, and then I've grouped together crater counting, gyrochronology, and radiometric dating here. And then in this outer band, that takes us way, way into the depths of the age of our universe. Uh, the green accounting for stellar spectroscopy, asteroseismology, redshift dating, and CMB radiation. So I wanted to build a companion to the cosmic ladder. Here it is. I'm sure the artistic work could be improved, although I do love my Salvador Dali clock in the middle that is glowing with this red radioactive glow around it. Okay. Now, just a couple of words about references and then we're all done. So I did use Chat GPT and Gemini, two AI programs, for this presentation. Just wanted to make sure I was clear on my intentions here. Um, Great tools. I use Chat GPT and Gemini more as research assistants. I would say, hey, go find different techniques, help me frame up this presentation. But I was careful to get that information back and cross-check it as much as I could. So they were great for doing a lot of grunt work, but at the end of the day, you really have to convince yourself by using other sources that what they're telling you is true. In a couple instances, they gave me conflicting information. So, you can see that even when you're learning subject matter material. So just wanted to make just a truth in advertising uh, statement there. And then lastly, Astrobytes. It was a great blog that I ran into. It's written by graduate students for undergraduates, very accessible, and was able to draw on that as well. And so with that, I thank you. And I will go ahead and stop sharing and see if everybody's still there. Yeah, it looks like people are still there. That's nice. And I don't see anything in the chat. So, with that, let me just open the floor up for any questions that anybody may have. And you just come off mute and ask your question, and we'll go from there.
I'll
Is
take a
that
stab at it, although I feel like at this level, much lower than a novice. But does the initial condition of the cloud from which stars form affect the geochronology measurement?
um,
Or do they all?
I think that those clouds are, well, certainly the clouds will impart some angular momentum to the
Right.
star. The
Yep.
degree to which that influences its rotation, I really don't know. I don't have a feel for that.
Okay.
But it is a good question. And I unfortunately don't have an answer there.
Fair enough. Thanks.
I had a question. So the related to that, so the cry the, the
Gyro?
gyrochronology, how
Yes.
was that actually measured? Was it also inferred from spectroscopy, or was there a different first principle to measure the rotation of a very, very far away star?
So with gyrochronology, you're using really precise, high-powered photometric equipment in these space observatories. So if you think about the tools used to detect exoplanets, it's really kind of the same thing, only here you're going after star spots in order to measure that rotation. And
Okay.
I would assume too, where you had an exoplanet, um, you might be able to get a handle on its rotation period as well, but I'm not 100% sure there. But it's measuring those spots on the surface by dimming of brightness.
Yeah. Yeah. Thanks. Yeah.
Anybody else?
You mentioned that the PhD student or candidate was looking at white dwarfs and was able to observe the G. Can't remember what they were called, G pulses as opposed to
The
P.
G gravity waves?
Yeah,
Yep.
the gravity waves, the pressure waves.
Yes.
Do they manifest differently? How do you distinguish one from the other?
Well, in the case of a white dwarf, you really don't have pressure waves anymore because you don't have all you
Um,
don't have the degree of turbulence like you did in a main sequence star. you still do have stuff going on in a white dwarf, but because that convective layer is now so thin and dense, you're able to detect those gravity waves.
All the pulses are assumed to be gravity waves. That makes
Yeah.
sense.
Yeah.
Thanks.
All right. Anyone else? I know it was a lot of stuff, but I got into this thing and I couldn't stop, so I just went for it. Like I'm sure you guys, you're probably sitting out there and your heads are swimming a little bit. And I can empathize with you because it takes a while to really get your head around this stuff. But anyway, I thought it was pretty neat. So, okay, well, listen, um, if there are no other questions, I'm going to go and do my famous going once, going twice. And I want to just close out the meeting then. I do want to say one thing before I sign off, and that is um, this is one of the things I really enjoy about astronomy. It is, there are just so many avenues that you can take to study and learn. And I really got a lot out of it myself by going through the exercise. So, that's one of the joys that I get from the hobby, and I hope that came through in the presentation because I really I'm happy to have presented it to you all here tonight. So with that, I will again thank you for your kind words in the chat. I appreciate that, and I will see you in September. And again, you thanks for attending, and have a great evening.